Welcome to our low-energy building analysis of the Frick Environmental Center, which is designed by renowned architecture firm Bolin Swinsky Jackson. This video is proudly presented by Kang and Pang Wei-Yun. Known as a living building that is open to all, it is a 3-story environmental center which aims to create a building that using just the water and energy resources collected on-site to operate. Located in Pittsburgh, US, the construction of the building was completed in 2018. The site size is approximately 17,000 meters squares, and the gross area of the building itself is 1,530 meters squares. It was awarded with the LEED Platinum certificate, achieved the Living Building Challenge, and 8 other appreciation awards. The following are the criteria the building mainly focused on to reach the mentioned achievement above. It is known as a net zero building as it is able to support its own needs for water and energy. For the reusable energy-wise, it has 2 main focuses, which is the solar panels and the geothermal heating and cooling system. It successfully achieved 48% less energy consumption than a typical building of its size. Looking into the sun path of the site, the building is in the north-south orientation and the prevailing wind is from the southwest direction. The building is perched on the edge of a south-facing slope. The energy-neutral insulation of the Frick Environmental Center is aided by the south facade, which is full with windows and decks. Wetlands and dense woodland in front of the front facade also help to maintain a cooler temperature in the building. The massing of the building is designed with a condensed massing with a maximum opening space. This is to enhance the natural ventilation and daylighting, at the same time aids in avoiding the heat loss during winter time. The front facade is able to receive maximum solar radiation during winters, as south building facade has the advantage of receiving more solar radiation during winter than during a summertime. A skylight tower was planned at the north side of the building to direct more sunlight, as the north facade is shaded for most of the time. As shown, the longest front facade faces the direction of the prevailing wind and the cooler air temperature of the wet and damp land. It creates a chilling effect provided by the fenestration of the facade, which are the floor-to-ceiling windows. The primary spaces were centralized in the building to against overexposure to the sunlight, at the same time to ensure the indoor climate to be more comfortable against overheating. The orientation open space was located along the facade in order to utilize the daylight through the full-height window on the facade, at the same time to reduce the usage for artificial lighting. The material of the primary building envelope of the center is natural and regionally sourced. All materials has undergone an extensive vetting process and were sourced from responsible industry, mostly recycled or local product. There are a few main types of primary regionally sourced materials used in this building, which includes steel, concrete, stone, aluminum, and black locust wood. Black locust wood is a regional wood that does not require treatment, stain, or sealant. It resists rot for 100 years or more. It is free of chemicals and rot resistance, which is perfect for exterior which lasts for a lifetime. The curtain wall is largely composed of locally harvested black locust wood panels and some insulation layer to achieve the thermal insulation during the winter period. There are some PCM louvers panel along the north gallery facade and south and west living room. It is an organic phase change material, possesses the ability to absorb and release large quantity of land heat. The efficiency of it has been tested scientifically in many applications. The automated skylight was planned at the north facade as it aids in maximizing natural light in buildings, at the same time particular interest in temperature, especially during winter. During winter, lower levels of natural illumination and higher cloud cover create the need to capture more light within the buildings. High solar reflectance index materials were used on the roof to reduce the heat island effect by reflecting sunlight and heat away from the building and reducing the roof temperature. It results in a more comfortable ambient temperature in the building. There is a deep overhang along the south facade in order to minimize the solar gain for both summer high-angled sun and winter low-angled sun. The use of the overhanging eaves allows for the natural cooling of the structure as well as the continued use of balconies during inclement weather. Ventilation. The building is laid out in a way that encourages natural ventilation, as the overview shown here. The prevailing summer and winter breeze blows towards the front facade of the building, brings in the cooler air from the wetlands, and a triple volume stairs tower to create a stack effect in the building. A red-green indicator light system which used to detect what the weather conditions are outside of the facility was applied in the building. When the outside condition is optimal, the green light will come on to alert the occupants to open the windows, take advantage of the great conditions outside. Vice versa, when the outside condition is non-optimal, the red light will come on to alert the occupants to close the windows, avoiding the bad conditions outside. Furthermore, integration of different ventilation system was applied in the building. The enthalpy wheel is an energy recovery system which is to transfer the outgoing temperature and humidity to the incoming outdoor air. It allows both heat energy and moisture energy to be exchanged in order to achieve the thermal comfort in the building. Besides, VAV systems vary the airflow at a constant temperature. The advantages of VAV systems over constant volume system including more precise temperature control, reduced compressor wear, lower energy consumption by system fans, less fan noise, and additional passive dehumidification. Lighting. For natural day lighting, there are floor-to-ceiling windows to allow sufficient natural light, reducing the need for electric lights. Large windows is aimed to provide natural light for classrooms, office space, public meeting spaces, and stairwells. For artificial lighting, a lighting control panel with a timer function is applied in this building. During the daytime, the light will switch off automatically, whereas during the nighttime, the light will switch on itself. At certain times, controlled lights will turn on, off, or dim to either save energy or to support changing space function. Low carbon transport. The center is highly accessible by various transportation, which is by walking to the center with bicycles, cars, and public transportation. The estimated occupants who commute via alternative transportation stands around 45%. The walkability score is at 70, which means most errands can be accomplished by foot. This allows an increase in program participation, which stands 142%, as only walking is allowed in Frick Environmental Center. Transportation-wise, the center has access to 3 lines and routes of bus with a nearby stop which needs a short distance of walk. It also connects 8 distinct city neighborhoods through an interwoven system of public trails. With the ample street parking and sidewalks, visitors can be led directly from the neighborhoods to the site's entrance. The estimated annual carbon emissions associated is around 11.46 metric tons, which is equal to 2 average cars, while an average car can already be emitting 6 tons of CO2 annually. Waste management. The center diverts 99% of construction waste from the landfill. It uses a simple material palette, prioritizing the use of natural and regionally sourced products. Here are some fun ways of how the center reuses construction waste on site.
Renewable energy. This shows the overview of sustainability features on site. Focusing on 2 renewable energies, the center uses solar energy with their photovoltaic cell feature and geothermal energy with a borehole system underground. These energies generated on site helps to create a net zero facility whereby 100% of the project's energy and water needs met. The on-site renewable energy resources supplies to all electricity as in artificial lighting and ventilation, heating during the winter and cooling during the summer for both air and water source. The energy data of the center during 2017 and 2018 is collected with their total energy supply and use. With a total of 327,912 kW per hour of energy collected, a total of 237,623 kW per hour of energy is used, allowing a total net of 90,289 kW per hour energy exceeded, which makes the energy demand collected on site stands 122%. Focusing on the photovoltaic cell, the feature on site is a PV solar array, which is a number of individual PV panels electrically connected together. From cells to module, then to string, and finally forming an array, the large photovoltaic array provides enough energy to more than 100% of the building energy needs. The photovoltaic system is tied to the grid but is net metered to ensure compliance with net zero energy goals. The photovoltaic array is a 161 kW solar PV system, allowing electricity produced on site. The center's predicted net energy use intensity was just 2,000 British thermal unit per second per square foot per year, which is 60% below average for similar structures, while the actual net energy use intensity came in at negative 700 British thermal unit per second per square foot per year, having an energy surplus which is then sent back to the grid. As said, the solar energy is collected at the parking canopy, where the solar panels shades the parking lot at the Frick Environmental Center. They are expected to generate about 150,000 kWh of energy per year, which is approximately 10,000 kWh exceeding the building needs. The excess generated energy will go right back to the electrical grid. The solar panels feature also helps to keep cars cooler. The distribution of energy produced from the PV array leads to the HVAC system, lighting features, the building's general purpose power, portable water pump, heating system, the elevator, and the barn. Another energy generated on site is the geothermal energy, which is thermal energy derived within the subsurface of the Earth. Starting from the ground source system, a series of connected pipes buried vertically, it then circulates a fluid that absorbs heat from or relinquishes heat to the surrounding soil. It then moves to the heat pump, which removes the heat from the fluid in the earth connection, concentrates it, and then transfers it to the building. Lastly, to the distribution system, with a conventional ductwork used to distribute heated or cooler air throughout the building. This shows the wide view of how geothermal energy process, accessed starting from the ground loops, which transfers heat to a working fluid in the heat pump, which then transferred to the building using the radiant flow tubing features, allowing spreading hot-cool temperatures. The geothermal energy on site is the heart, located in the center's basement. The center taps 18 geothermal vertical bores on its 4 acres property to precondition the water for radiant heating and cooling system that runs throughout the building. The geothermal bores are 525 feet into the ground. One set of the pipes sends 65-degree water into the ground, while another set brings cooled 60-degree water back into the building. The geothermal well valves are purposefully left exposed to spur conversation about sustainable heating and cooling process in the center. The 8-ton heat pumps involves both water-to-water source and water-to-air source. This allows conditioning the air and water based on transferring heat into the ground or taking heat from the ground. Water management. The center is net zero water by engineering an advanced water collection and storage system, designed to use approximately 330 gallons per day and has an on-site water storage capacity of 17,500 gallons. Their net zero water strategy is the rainwater harvesting system. The rainwater is stored and collected by harvesting it from the large photovoltaic array canopies. An infiltration basin is also featured underground of the parking area. Rainwater infiltrates through the ground with pervious pavers. Then, the rainwater is passed through above-ground rain barrels, which is also used for watering purpose for demonstration gardens. The remaining rainwater is then collected into a 15,000-gallon underground cistern. Then, the stored rainwater is treated and used for potable and non-potable water inside. Non-potable water supplied include toilets, urinals, historic fountain, and landscape irrigation. The center also features solar-powered self-generating faucets and flush valves. At the northern edge of roof exists a 40-foot long rain well, where rainwater runs off the roof, cascades in a dynamic curtain of water, visible from the interior and exterior. From there, the rainwater channels into the rain ravine. The rain well, with the center's simple sloped roof, the rainwater falls in a dramatic sheer curtain, allowing visitors to interact with water. The rain ravine. It is a stepped sandstone water feature evocative of the sheer geology of the region. The water meanders down the hillside, continuing its journey to the wetlands below, restoring the Nile Mound run. 636,000 gallons of stormwater is diverted per year, and 80% of total suspended solids are removed from the rainwater capture. All water usage is submitted and recorded by BMS. The net zero techniques implemented. Firstly, in wastewater treatment. Wastewater is treated and discharged on site using an underground treatment system and drip irrigation field in 3 phases, separating waste solids from water with 12-volt septic tank, then a recirculating sand filter, lastly going through a UV disinfection and discharge through a hydraulic control unit, reducing water use and demand with ultra-high efficiency pumping features, in arts with the rain ravine feature, in community congregation with the minimal use of water volume for the historic fountain, and finally in agriculture with the use of rainwater and wastewater for drip-filled irrigation together with planting of native plants which is tolerant to thrive. Post-occupancy. The energy collected on site is 328,000 kW per hour of energy in 2 years, while the energy consumption is 238,000 kW per hour of energy, which is only 72% of the total energy collected. It proves that the building has successfully created an energy surplus. The consumed energy usage intensity per square foot per year only stands 76.6% compared to predictions. The net energy usage per square foot per year is negative 35% compared to predictions. The reduction from natural average EUI is predicted at 60%, while the actual exceeds at 101%, while the net carbon emission per square foot per year is negative 3% compared to predictions. Data collected during January 2018 shows that even in the harshest conditions, the building maintained optimal occupancy temperature for several hours without using an active heating system. During winter, it allows geothermal heating system to stay off for several hours each night, while during summer, it is able to stay cool overnight with less energy usage. Findings from a post-occupancy survey shows that overall employee experience happiness, comfort, and productivity as the following criteria have led to a more comfortable work environment, which is temperature, ventilation, and humidity regulation. Staffs feel more collaborative, creative, and relaxed, leading to a superior work experience. Conclusion. Rounding up, Frick Environmental Center excels as a building, which it is a building which is living. It achieves a LEED certification with Platinum, scoring a total of 86, which proves that Frick is a net zero building. It's the first municipal building free and open to the public in the US to achieve Living Building Challenge certification. In conclusion, the Frick considers spaces with functions, highlights the planning of spaces and optimizing daylighting, materials being environmental friendly, in ventilation integrating different low energy consuming ventilation system, maximizing the usage of daylight, reusing construction waste, being highly accessible and walkable, involves the application of geothermal borehole system and photovoltaic arrays, reusing rainwater harvesting as water supply. That is all from us. We hope you enjoyed the experience of Frick Environmental Center. Thank you.